Hey everyone, my name is Mohit, and today I'm going to be talking about fast and secure text generation systems. So one common paradigm is, as a company, you might have an NLP model that you would like to host as an online service for users to query, and users can pay for these queries. So we have things like Google Translate or Allen NLP's web demos and so on as examples of this. And all of these setups follow the same general pipeline in which we have this kind of black box model in which users submit queries. In this case, I drove to school, and users do not get to see any details of the model. They don't need to know, the architecture or the algorithms that underlie the model. They send their query to the model, and they receive some output. So in this case, they receive a German translation of this sentence. So in this talk, we're going to discuss a couple of key considerations when you think about this pipeline. So the first is that it's becoming increasingly more common to deploy text generation models in these kinds of pipelines. And text generation models have been rapidly improving over the past few years. So you might have seen, for example, very recently, OpenAI's GPT-3 had a lot of headlines because of partly because of its impressive text generation capabilities. And a trend that you might have noticed is that text generation architectures are growing increasingly large, and they're requiring increasingly more compute to actually use. So if you're going to deploy a model like this, you should be concerned with the latency of your model, right? If a user sends a query to your model, they can't be waiting forever to receive the output from this model. They just won't use your feature in this case. But it turns out that most of the fancy models we have today are too complicated and too large to serve efficiently with reasonable computational resources. So one of the things I'm going to talk about today is how we can develop models that are faster to generate text to minimize this latency. Another thing that I'm going to talk about is the security of the models that you put on that are served by these APIs. So you might think that just because your model is a black box and the users don't know any of the details behind it, that it's perfectly safe. But it turns out that that's not actually the case, and that users who don't even have to be particularly clever can, for not that much money, steal the models that underlie your API. So these two aspects, the speed of the models, their efficiency, and their security, are what I'm going to be talking about today. So as an outline for the rest of this talk, I'm first going to introduce an example task that will serve to highlight these two challenges. And so this task is story generation. This is a nice task because it involves generating large quantities of text. And we have an actual user-facing system in which latency is a very real concern. Next, we'll switch over to a more researchy discussion of the standard model architectures that are used in text generation tasks today, and how you might modify these models to increase the speed at which they generate words. Finally, we're going to talk about these security vulnerabilities that I alluded to earlier. Okay, so right, let's jump into this task of story generation. So here, we're basically asking a model to produce a story given some input prompt or context. So as an example, here's a prompt. Flowers have become so rare that they're the most sought after items in the world. They're sold at high prices in black markets, and you just stumbled across a natural rose. So I might give a model this information and ask it to produce an entire story or part of the beginning of a story or something like this. And you can see that, this is just like the first 4 paragraphs of a human written story in response to this prompt. And it goes on for, many, many more paragraphs. But there's already some interesting high-level structures in this story that any text generation model might want to be aware of when it's producing its own stories. So I'm not going to read this whole thing out loud, but essentially it starts off by describing the setting of the story, which is in some sort of desert-like environment. And then it introduces a character. This first-person narrator, I, had been the first to stumble upon this rose. Next, it proceeds to lay out more setting, introduce some more characters, like secondary characters, people in this village. And then finally, it introduces this concept of a biodome, which makes the story kind of fall in this science fiction type direction. Once you read this, you want to know, what is a biodome, what is associated with that, and how is the story going to unfold. So if you think about it, the task of generating a story can be broken down into, producing these separate elements and tying them all together. But importantly, this unfolds over a large number of words, right, of sentences, of paragraphs. And if you're generating an entire story, you need to be aware of how long it's going to take the model to produce this text if you're going to actually show it to users as a feature. So in this case, here's an example of what is produced by the prior state-of-the-art language model GPT-2. Now, of course, we have GPT-3. But you can see that this task is not trivial, right? So this generated text is pretty bad. It's kind of not a story at all, right? But rather some sort of advice about how to take care of plants. It even gives you these links, which are not actual links, by the way. These are not websites. They just look like it. So there's a lot of work to be done on the modeling side to make sure that what the model generates is actually a relevant and enjoyable story. So this is an extremely hard task, which is why I think it's exciting and why my group works on it. And there are many different challenges that we've talked about to this point, right? There's this planning process. How do I connect things like the setting and the character development and the narrative arcs together? And we also know that stories can be really long. So in contrast to a task like machine translation, where I might only have a single sentence as input, stories, they can be full-length novels where we really don't have the capacity at this stage of natural language processing research to produce such units of text. So it's hard to work on this task, but it's really awesome to see that in the NLP community there's been lots of interest on story generation over the past couple of years. And so what I'm going to introduce now is our work on machine-in-the-loop storytelling, and this is where it starts connecting with deploying language models to users and all of these concerns that we talked about at the beginning. So in a machine-in-the-loop storytelling setup, we have a human writer who has maybe an idea for the story that they want to write. But maybe they're stuck with writer's block, or they don't have any idea of how to continue what they've written up till this point. And so our idea is that when they get to this point, they can click a button and ask a model how it would continue the story. And then they can use the model's generated text as inspiration for whatever they want to write in the future. So in this case, our black box model is the story generation model. So I'm going to get into now a little bit more about the data sets that we use to develop this model, and then talk a bit at a high level about the modeling architectures before focusing on how we can make them faster, which is one of the main points that I want to make here. So this work was conducted by my PhD students, Nader and Shufan, and Nanyun Peng, who's my collaborator, assistant professor at UCLA. So we partnered with this web platform called Storium, which is a place where people can go to essentially learn to write stories together. And the way that Storium works is as follows. So a small group of users will join up together and write a story together. So if you see here on the left, we have a cast of characters. So in this cast, each of these characters is controlled by a different user. And there's another user who acts as a narrator. So the narrator is the one that kind of guides where the story goes. The narrator introduces challenges that the characters need to solve and introduces subplots and subgoals and so on. So let's take a look at one of these characters. Here we have Emilia Lopez. You can see that this biography of Emilia Lopez introduces a number of abilities or properties which are called cards. So Emilia is a lab technician. You can see here on the right, she works with chemical and biological lab equipment. Some of her attributes include good hearing and curiosity and so on. So the one user would be controlling this character of Emilia Lopez and writing scenes from the perspective of this character. So, what is actually the plot that these stories are following? Again, the narrator is the one that defines the plot, and basically they do this by creating challenges that the characters should solve. So in this challenge, it's called Hit the Books. And so if we click on it, we see that the challenge is you have your personal libraries, the internet, and the public library, time to research what you can about werewolves. So this is what Emilia Lopez is supposed to be doing for this particular scene, and she's going to be using her curiosity attribute to address this. So this is the kind of data that we have, and the goal here is to generate the scene conditioned on all the different types of contexts that we have. So our model's goal is to produce this text. Okay, so if we zoom out a little and look at this this website, it has about 30,000 active users, 6,000 or so different games have been played. So a game in this context is the same as a story. And there's over 100 million different words in the data set. So it's a fairly large data set and pretty interesting, but mainly we're concerned about the number of users, because this, if we're going to deploy models to the number to thousands of users, then it's going to put a pretty big load on our servers, and so we want the most efficient models that we can have. So yeah, this is kind of leading into our evaluation methodology, in which we design models to generate these scenes conditioned on the different types of context, right? So what character is addressing the challenge? What is the actual challenge? What attributes does this character have? And then we allow users to click a button and generate a suggestion from our model based on whatever they've written up till this point. And then they can edit it however they want. They can even completely delete the whole thing, which, as you'll see later, they do frequently. And then we collect the edits that they make on the generated text. And we can use this to evaluate our models, but also at some point in the future, we'll be using this to train models on the user's behavior. Okay, so at a high level, our models are fine-tuned versions of large language models. So these are neural network models that are trained to, given some amount of text, predict the next word. And so for this work, we were using GPT-2. Obviously, we hope to use GPT-3 also in the future. But again, this is a model that is enormous and likely beyond the capability of the machines that we have at UMass. So maybe it'll take a while before we're able to get to that point. But anyway, as I mentioned before, a language model is trained to generate the next word given a preceding history of words. So In this case, our preceding history is formed by concatenating all these different types of contexts together, right? We have a challenge, we have a character with a biography and some attributes, these cards that they might be using. And so we don't do anything fancy. We just concatenate all of these things together. We have a separate segment embedding that is used to help the model differentiate these different types of contexts. So all of the words in the challenge will be associated with this green marked segment embedding. All of the words in the character context will be marked with this yellow one, and so on. And then we just fine-tune our language model on the entire dump of the Storium website. So we have different variants of this model. We have one where we add more context, including entries that happened in the past, not just the current entry. This is actually a major limitation of these models, is that they have fairly small fixed length context limitations. So GPT-2, I believe, has a 1024 token limit, which means that you cannot model contexts that are longer than that number of words. So when you're dealing with something as complicated as a lengthy story, this is not sufficient. But we're not going to be talking here about how you can address that, although this is something that my group is working on at the moment. So before we get to the speeding up these models, I just wanted to share briefly how users actually interact with our models. So we deployed the model that I just mentioned onto the Storium platform, and when users decided to preserve parts of the generated text in their final stories, they tended to keep short phrases from the generated text. So here we see names like Chang Wei are preserved, but all of the text that's not green and bold here is new text that the user wrote. And the green bolded text is stuff that they decided to keep from the generated text. So it's not like they're keeping the entire suggestion and adding on to it. They're deleting lots of it and keeping things that maybe sound good, short phrases. And so this is what happens usually when they decide to keep stuff, but almost half the time they decide to just delete everything. So this is obviously not desirable, but it also shows how challenging this task is, right? So in this example, the model generated the top paragraph based on some context, and the user created the bottom paragraph. So there's no overlapping n-grams or words here, other than things like names or stop words. So this indicates that the user found the generated text to be not useful at all. And obviously, one of our research goals is to make instances like this to reduce the occurrence of this kind of behavior. We want the generated suggestions to be useful and inspiring, and so that this is a kind of modeling challenge going forward. So if you're interested in learning more about the Storium dataset and platform, we're planning to release this over the next few months to anyone interested in building models and deploying them on this platform. So for free, you are going to be able to take your model and plug it into Storium and have the users interact with your model. And we're going to set up a leaderboard to compare different models on this kind of human evaluation metric. Okay, so this was our kind of case study, but I just wanted to turn to the challenges that we faced in integrating our models into the Storium platform. So this has been really a huge engineering effort on the part of my group. And as I've mentioned multiple times now, one of the most important challenges was the latency. So how long do the users have to wait before they receive the output of the model? And the developers of the Storium platform told us that if users are consistently waiting more than 30 to 60 seconds to get the outputs of the model, the users are not going to like it, and the developers are not going to allow this feature to be deployed on their platform. So with 30,000 users, and we have maybe 4 to 8 GPUs dedicated for this service, it becomes, pretty infeasible to maintain a reasonable latency with when a large volume of queries comes in. So this kind of launched a side project in which we started to investigate further the model architectures that we were using in this setup, just to see if there were changes that we could make to speed them up while still maintaining their performance in terms of the quality of the generated text. So here's a quick timing comparison, just to kind of motivate why this is an important problem. So these numbers are produced from a machine that's running a single 2080 Ti graphics card. And we're particularly interested in this last row of the table where we're generating 300 tokens. This is about the average length of a scene in the Storium dataset. And the last column, so this bottom right cell here, where the model has 300 tokens of input context and 300 tokens that it's going to produce. So you can see that already on just a single GPU with no other load in the machine, it takes 10 seconds to do this. So if you have an application where you want to generate thousands of words from your model and you want it to be conditioned on thousands of words in turn, this time is just going to blow up. And this is especially true because the model architectures that we're using today have elements that quadratically scale with the length of their input. So that's what I'm going to be talking about next. So this is work that my students Wei Chu and Simong did that was presented at ACL this past year. And here we're focusing on specifically the transformer architecture, which is the current state of the art for text generation and basically every other NLP task at this point. And the transformer relies heavily on a self-attention mechanism. So I'm going to explain how that works in a second, but essentially this is what's making at least a large contributor to the slowness of these models. Self-attention is quadratic in the input length. And so we were motivated to figure out if we can replace it with something that is much faster. Okay, so just as a review of how self-attention works, I would encourage you, if you're not familiar with this topic at all, to read up on it, as it is probably one of the most important concepts in natural language processing at the moment. But essentially how it works is that if you have a sentence, so here we have this input sentence, Nobel Committee awards Strickland, who advanced optics. We're going to represent each of the words in the sentence with a separate vector representation, which is also called as an embedding. So if you look on the bottom of the page here, you see these black circles that are in black rectangles. These are the initial representations of these words. And now we want to get a contextualized representation for each word. So this means for Nobel, I want a representation that has some knowledge of all of the other words in the sentence. So to do that, I'm going to take my representation for Nobel and project it into 3 different vector spaces. So I'm going to essentially get a query embedding, a key embedding, and a value embedding for every single word in this sentence. So what are the functions of the query, key, and value embedding? They're essentially there to compute scores of how important each of the other words is to understanding this, the current word, Nobel, and how much we want to weight each of these context words when we produce the representation of this word to feed to the next layer. So how does this work? Let's say I'm looking at this word Nobel. I take the query representation for Nobel, so that's this blue vector here, and I take the dot product to all of the key vectors for each word in the sentence. So here there are 7 words in the sentence, so I'm going to have 7 scalars as the result of taking this dot product. And that's just for Nobel. So I'm going to do this for every single word in the sentence, take the query vector for the word and multiply it, take the dot product with each of the key vectors. And then I'm going to normalize all of these. So I'm going to get essentially a probability distribution over all of the words in the sentence for every word in the sentence. So you can see here where the quadratic complexity comes into play. So I'm going to use this representation to take a weighted average of the value vectors, and then that is going to form the input to the next layer of my model. So transformers are essentially this exact computation that I've just shown, but stacked into many, many, many layers. You might be familiar with the BERT model, for example, which is 12, 24 stacked layers of self-attention. So this is a very important concept, but you can see that it is quite slow because we have to do this projection and then compute this dot product for every single word between every single other word in the sentence. Okay, so we were looking at this and we decided to think about this question. So in the vanilla transformer, all of the attention scores, these weights, are learned, right? They're the output of the dot product between the query and key vectors. But what if we inject some sort of inductive bias into this model, and instead of learning them, we simply just hard code the attention score? So regardless of what word it is, we're going to assign the same exact weight. How much does your performance degrade if you do this? So just to be clear, in this hard-coded self-attention, we get rid of the query and key vectors because we are not going to be taking this dot product anymore. Instead, let's say I'm at some word of the sentence, maybe Strickland. I'm going to take a hard-coded distribution that's fixed, it's not learned, and I'm going to just use it to compute a weighted average of the value vectors, and then feed that as a next representation to the next layer. So the idea here is that we believe that local context, so if I'm at Strickland, I might think that the words closer to Strickland are more important than the words farther away to Strickland. So words like awards and who are more important for its representation than words like Nobel or optics. Of course, this is not true in general, but it's hard to know what is really happening when you have a 24-layer stacked representation, right? If you are stacking this kind of local hard-coded attention, eventually your effective receptive field is going to cover all of the words in the sentence after you reach some number of layers. So it is unclear exactly how much value learning the self-attention gives you over just simply hard-coding it. So we designed these hard-coded attention heads that are basically hard-coded. Their distribution centered around different words in the sentence. You can also view this as equivalent to a one-dimensional convolution with a fixed kernel. So the fixed kernel here is this hard-coded distribution. And so if you look at the internals of the transformer, there are 3 places in which you can replace the learned quadratic self-attention with this hard-coded, much faster attention mechanism. So there's an encoder, a decoder, and there's a cross-attention between the decoder and the encoder. So this is for a sequence-to-sequence modeling framework. And we're going to look at this in the context of machine translation. But in general, self-attention is used in every single transformer-based application. So you can always think about replacing the self-attention component with this hard-coded variant, regardless of what application you're talking about. So we looked at machine translation in particular, and we found that the self-attention is actually not incredibly necessary for the learned self-attention. to get good translation quality. So in machine translation, we measure translation quality using an automatic metric called the BLEU score. And we looked at the BLEU score evaluated over many different data sets. So we have English to German, German to English, English to Romanian, Romanian to English, and English to French. We also looked at other languages like Japanese. But you can see that the second column here is what you get when you use a normal transformer model with all of its normal learned attention. And then when you hardcode the self-attention, that is removing this ability for the model to actually learn which words to focus on and which words not to focus on, there's no significant change in the BLEU score. So you can see that for some data sets, it even improves slightly over the learned model, while for others, it decreases a little bit, but these are not significant changes. So what this means is that we can completely replace this quadratic complexity mechanism in the transformer model without impacting the quality of the text that it generates. So how much does this buy us? So there's two things you want to look at when you're making your models more efficient. One is the speed, which we've talked about before. So by doing this, making this change, we were able to increase the decoding speed. So how many sentences you can translate per second by over 30% compared to the baseline transformer. So actually, we were hoping that this would result in a much larger gain, but 30% is still nothing to sneeze at. The other thing that's important is that you can increase your batch size when you do this, which means that when you get rid of the learned self-attention, your model requires less memory. So this is important if you want to improve your efficiency at training. So just to conclude this section, if you're faced with a task that you want to deploy to actual users where latency becomes a concern, you can consider making fairly drastic simplifications to models like the transformer without incurring significant performance loss. I want to emphasize that these models are very new, right? There's new advances coming out every week, basically, in NLP, and so oftentimes they have a lot of extra complexity that have not been properly ablated, or people don't quite understand which components are necessary and which aren't to obtain some level of performance. So if speed is important for your task, you can consider making dramatic simplifications without, because in many cases, researchers may not have tried this, or they may not exactly understand why their models are working so well. Okay, so I want to shift now to the second and final part of this talk, in which we'll be discussing security concerns of this kind of NLP pipeline that's becoming more and more common these days. So if I have our pipeline where users query a black box API and receive the output of the model, you might think that this is a completely secure pipeline because the model is a black box. The users have no idea what kind of model this is, and they don't have access to any of its parameters. They only see the inputs and outputs. But this is no longer true. And that's because all NLP models nowadays rely on the same broad principles, and in many cases the same pre-trained models. So things like BERT or Elmo or GPT-2 or whatever. It is at this stage, kind of foolish not to use these models because they've been trained on so much data using so much compute that normal researchers and people in industry can't access. So if you want to, get the highest performance on your downstream NLP task, you're very likely to be using one of these pre-trained models, or if not that, very similar looking architectures. So one thing that I want to discuss here is that this pipeline is vulnerable to model extraction attacks. So that means that a malicious user can, with a relatively low number of queries and for very low cost, steal your model with and the model that they steal will achieve very similar performance to your precious model that is served by your API. Obviously, this is not desirable for anyone who's deploying their models in this way. So this work was presented at iClear this past year and was primarily done by my PhD student, Kalpesh Krishna. All right, so here, just to simplify things, we'll turn from our text generation setting to a very simple and standard NLP task of sentiment analysis. So in this example, the user gives a query like, this is a great movie, and the model is supposed to predict positive or negative. So it's very commonplace nowadays to use BERT, which is a transformer model. So we just looked at transformer models. That's been pre-trained on billions of words of text, and then fine-tune it for your downstream tasks. So in this case, sentiment analysis. So if you're serving a sentiment model, you're very likely have some sort of BERT-like thing behind your black box API. So we're going to call this the victim model. And if I have a malicious user, the malicious user's goal is to steal the victim model. That way they can perform the same task of sentiment analysis on all of their data for free, right? Because they no longer have to pay you to use their API. There's obviously also more malicious use cases where they deploy their stolen model and charge others to use that. But I'm not going to get into what a malicious user could be using this for. Okay, so we decided to start with, what is the dumbest way possible to steal a model? If you're just a single user and you only have black box access to the model, basically all you can control is the queries that you send into that model. So one thing that we decided is to see what happens if you just send random gibberish sequences of words to the black box model. Of course, regardless of what you feed in, you're going to get some sort of prediction, right? So I can feed in 17 I period miles Vegas. This means nothing into the black box model and observe that it predicted positive. So in many cases, I won't even get a probability distribution to tell me, what percent positive did the model think this sentence was. I might only observe that it was positive. So similarly, I can send another garbage query, circle forward had support period, wife rulers, blah, 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 and I receive a negative label from the black box. And I can repeat this, n number of times, where n is thousands of times. And now I've actually created a sort of fake training set, right? I have these gibberish queries, and I have the predicted labels from the black box model. So now I can just take a pre-trained BERT model, which is freely available. It's very easy to fine-tune these things on your own data set. Actually, one of the other speakers from Hugging Face has a whole library that makes this really easy, so props. So I can take my fake training set and fine-tune one of these pre-trained language models on it, and this is going to be my stolen model. And it turns out that this actually works really well, despite the fact that the model has seen no real queries at all. Okay, so then, we've already discussed why model extraction is a big problem, but one thing that's very interesting is that these attacks are financially practical. So we stole, the sentiment analysis model from Google's natural language API, which costs $1 per 1,000 API calls. So to achieve, very similar performance to the black box model, we only had to pay $62 to do this. So it's really cheap to get a model that's just as good as Google's own sentiment model. And yeah, smart attackers can even do more complicated things, including text generation tasks. So far we've looked at, what if the user is just submitting random queries to the model, and this is actually a desirable, from the attacker's perspective, method, because it requires no effort on their part, right? It's very easy to write a program that just issues random queries to some API. It becomes harder if you want to actually generate queries that look like they could come from the task. So for sentiment analysis, this isn't really a problem. If I want sentences or queries that look more like English sentences, I can just basically sample sentences from Wikipedia or just random websites and submit them as queries to the API. And this turns out to work better than issuing completely random sequences of words. But yeah, probably the most surprising result here is that you don't even need proper grammatical queries for this extraction attack to work. We've tried this strategy even for more complicated tasks, such as question answering, where a model requires two different types of inputs, a paragraph or document, and then a question about that document. And so we've generated random sequences of words to form a document, and then a random sequence of words to form a question, and been able to extract QA models from this this kind of fake data. So this is a very powerful attack. And so this is just showing those results. Here we're showing it on sentiment analysis, that's the SST2 column, textual entailment, that's MNLI, and question answering, which is squad. So here we've highlighted that the black box victim model gets a 90.6 F1 on the squad QA dataset. And a model extracted using random queries gets 85.8 F1. So, it's not great, but it's significantly better than a model that, say, doesn't use BERT. So it's still a pretty good result for a stolen model. And it's even more impressive because it has not seen a single grammatically valid paragraph or a question during training. But more interestingly, if you use the Wikipedia strategy, where you just retrieve random paragraphs and sentences from Wikipedia and query the model that way, you get very close to the victim model's performance of 89.4 F1. So that indicates that this is a very, very powerful attack. So I just want to conclude by saying that so far there are no effective defenses for this kind of model extraction attack. We examined a couple of different types of defenses, but they are easily circumvented by clever adversaries. So in essence, you should think twice before allowing users to have query access to your models, because regardless of what kind of task or how complicated your task or data set is, it's very likely that users will be able to steal your models. And just as an example of this actually happening, a follow-up paper from some other researchers, Eric Wallace at Berkeley, I shouldn't say follow-up, concurrent work, showed that you could apply these kinds of attacks to Google Translate. And so they actually were able to extract a machine translation model by querying Google Translate that performed almost as well on translation data sets, a variety of different translation data sets. So yeah, something definitely to be aware of if you're in the space of offering NLP models as a service. Yeah, that's it. And I look forward to answering questions at the live session later this week. Thanks.
Thank you, Mohit, for your talk, and thank you for joining Q&A session. And let's do the first question, and it's actually a rather general one, but I hope you'll be able to answer it. So in regards to talk more about metrics that you used for evaluation of text generation.
Yeah, so it kind of depends on the specific generation task. For things like machine translation, there are reliable automatic metrics such as the blue score, which rely on kind of n-gram or word overlap between what you've generated and some reference. But for more creative tasks such as story generation, there is no good automatic metric, and so you have to rely on human evaluation. So humans actually have to go look at the output of the model and provide some scores, but realistically, that kind of evaluation is also very unreliable. If you imagine asking someone, rate this text from a scale of 1 to 10, it's a very subjective evaluation, right? So that's why in our work, we've focused on this edit based measure where we provide users with what our model generates, and then we ask them to edit it in such a way that it kind of suits whatever they want to write. And our metric is based on the number of edits that they make. So if they delete the whole generated text and write their own thing, that's bad for our model. If they preserve a lot of the generated text in what they eventually complete, then that's good. So that's a maybe more reliable metric because it directly engages with the users who are interacting with our system.
And in regards to this kind of feedback, did you see some of the text fragments or prompts that were generated get more variation in the output versus others? Prompts getting less, yeah.
Yeah, so we saw one example of where our model succeeded in this regard was in generating names of characters. So we actually found that the users really had a hard time coming up with new names of people or places or things like that. And the model is, it's not that great at generating coherent text, but it is good at coming up with random names of people, and so they love that feature, which is not really what we wanted to hear, because we wanted to hear that it's producing new plot lines and cool ideas to take the story forward. But instead, one of the most useful things they found was its ability to generate names for new characters. So I think there's a long way to go in text generation research before we can get to a point where other things are useful.
And it's a really fun point about what people are like most striving with and that kind of stuff. And one more question in regards to text generation and control text generation. So are there any ways to force model not to forget the character's name and not to bring up different characters in each sentence, that kind of stuff? And the probably, or maybe some researches in this area, so related to text generation, which is coherent and logical, I guess.
Yeah, so I didn't talk too much about this in the actual talk, but there is a pretty large subfield now on generating more factual text. And so this means if I'm producing, say, an article, I might want the entities in the article to all be real, and I might want the properties that are exhibited in the generated text of those entities to be valid facts, right? I don't want to be hallucinating fake facts or making up things, especially in a more realistic text generation setting. So, but I will say that this is not a solved problem by any means. We have a lot of work that focuses on kind of linking text generation models with knowledge bases that have these links between entities and the relations between them. But at the end of the day, our models are all kind of soft. They don't have hard constraints attached to them. So it's very hard to add such constraints to these big neural language models. So and another thing that makes this challenging is the randomness that's present when you generate text from these models. So we need the randomness right now because if we don't, if we generate greedily from the model, we get all these artifacts like repetition of phrases or words or very boring short sentences. So the randomness also allows for hallucinating facts. So I think that's a big step going forward, is to figure out better decoding strategies that can be more faithful to facts.
Okay, thank you for this answer. So I think like we will do like two more questions, and that would be it. So one of those is actually in regards to real life applications of long form text generation and storytelling. Could you speak up to that?
Yeah, so I think at least my group's motivation is to kind of build a fully featured writing assistant. So of course we're looking at this in the context of the story generation task now because it's a concrete place in which we can get users to evaluate the models. But if you step back and think about it at a high level, you could imagine this kind of model allowing people to produce new ideas for even technical documents, or maybe more importantly, paraphrase what they've written if they're not satisfied with some text that they've produced. They can, have the assistant rewrite it in a maybe more stylistically relevant manner, or whatever pleases them. And then there's also other aspects that you can imagine implementing into such a framework, like we all know our email has these autocomplete features, but that could be far more powerful if you imagine giving your model some specific tags, like I provide an entity and then ask the model to autocomplete a kind of factual biography of that entity or something like that. So all in all, you can imagine many ways of making text generation, just the writing process by humans more efficient. And yeah, that's the high level goal for us at least.
Got it. Thank you so much. And I guess that will be it for now. I did hear that we had an idea of possibly grabbing the questions that still left unanswered, or if any of the viewers will have those, and sending it to Mohit and for you to answer. Yeah, I hope it worked. Yep. Thank you so much for today, and have a good one. Bye-bye.